Okay, so yeah, I just copied some notation in this morning. We have this Gaussian, so we are now, for all this afternoon, I at least until I hope, okay, most of this afternoon will be like finite dimension, okay? So you have a Gaussian measure in finite dimension. I could even write down density with respect to Lebesgue, okay? But will not tell you much more than what it's written here. All my Gaussian variable are centered, okay? So I don't specify every time because I think I never use in my life a non-centered Gaussian. Yeah, I'm sorry for the noise. Let me know if there are problems. I will try to change, but outside it's raining, so it's not an option. And then the goal is to construct stochastic quantization for this measure. Again, everything is well defined. Take V bounded below. And well, yeah, with finite mean, but okay, to think about of it, we will soon take V of, okay, I just think, okay, if you have problem, just think about this and maybe with a constant, okay? This is, all the course is about only this polynomial, okay? With lambda positive and the beta maybe anything or just 0, okay? If you don't care about, let's not care about beta for the beginning. Okay, so I just want to write a stochastic quantization for that, and unfortunately, even if the problem is quite simple, it's not so obvious how to construct a dynamic which has this invariant measure, no? And so the first step, let's consider stochastic quantization for the base dynamic and when we try to perturb. Okay, so the law is Gaussian, and then again, okay, so I want to construct a stochastic quantization. Okay, maybe I promised myself to give some historical references or references. Okay, I mean historical landmarks. So the stochastic quantization, if you want to know some name, was introduced essentially by the idea by Nelson, and then Parisi and Wu. This is a very cited paper, very much put in the physics literature. Rigorous construction of Euclidean quantum field theory with stochastic quantization was done in D equal 1 by Iona Lasinio and Faris. So this is like the 80s, okay? Maybe I will give later, I will give you a paper for the, let's say for the history, okay? So let me just write the name maybe in the 80s. And then Iona Lasinio Mitter, or Mitter, let's say, Iona Lasinio. Again, it's like 84, maybe. I don't remember exactly. Into dimension, bounded volume, and then Mitter et al. In infinite volume. Later on, for, let's say, just because so I don't forget to say the names right now, for D equal 3 and 4543, if you want. Yeah, no, sorry, 4542 2, but in general for polynomials. So let me use this notation. These are polynomial theories in 2 dimensions, okay? Let's say, so, and this was done using using probabilistic tools, if you know. Okay, so martingale problem and Giesano formula, etc. Okay, for P phi 2, a more another approach was introduced by the Prato and the Bush. And then, but of course, the three-dimensional case was open for a long time, and only in like 2013, Martin Eirer managed to prove a basic result, a local existence and uniqueness, result for this stochastic, the parabolic stochastic quantization of 543. Okay, so this is, and then from that, using regularity structure. This was the first very striking application of regularity structure. Okay. And from there were many more results. So for more detail, and then we had many more results until today. Okay. Still many problems remain open. Okay, so there is very interesting open problem. For more details on the history of Euclidean quantum field theory and stochastic quantization, look at the introductions of these two papers. Okay, so let me just put these two papers. So one is the paper I cited, which is the basic reference for this course. Okay, if you have to give a look at something, please give a look at this paper. Yeah, I don't know why it's okay. That does not recognize. So 543. And then the other paper, which contain also other historical remarks. So we took a bit of care to write down maybe these two papers. Okay, so let me just check. I want maybe the published version. Yeah, this one. I'm just citing my paper not because they contain, somehow we took care of write some, I mean, the introduction. Many people contributed and told us what was the history, and we tried to write it down for the people like us which you didn't know the history. Okay, and this history go back to the 70s, so essentially I was not even born, so other people had to tell us what really happened at that time. And so these papers, somehow, these three papers, okay. And they also show different kind of stochastic quantizations, okay? And then for hyperbolic and variational, hyperbolic stochastic quantization and the variational method, one could refer to, and then I give you other two papers. So maybe, so for the, sorry. Yeah. for some, yeah, I think you can give a look at this, for example. And then the variational approach is here. Okay. Okay, so let me put abbreviation for the names. Okay. If you have question maybe on this first introductory part, now we are going to please ask now, or any remark or maybe comments, or if you want me to stress something. Anyway, I think the history, the precise history, it's well written in this paper. We took care to write down a bit more detail. For also with respect to this morning, the discussion of what is known, it's very difficult. There are a lot of literature. Surely you can refer to the book of Glim and Jeffy for the two-dimensional case, because it contains a lot of discussion. For three-dimension, it's more difficult to find in papers. There are a lot of ways to construct 543. And here we make somehow a review in the introduction about the methods and the ideas. And in this paper, we look, so in this paper, I didn't mention yet, because somehow this enters into the situation where the stochastic quantization is not made via a probability measure, okay? But somehow the interest to me of this paper is that we want to look at a situation where you don't have a probability measure in the classical sense. We want to interpret it as a situation where you can anyway see the problem, and stochastic quantization as a problem in non-commutative probability, okay? So the only shift you have to do is that instead of looking at probability theory, you have to look at non-commutative probability. But okay, it's not the point of this talk, okay? So I think for introductory remark and for all the bibliography, please look at this paper, okay? There are like more than maybe 200, even 200 citation references in this paper, okay? Good, so let me just, I don't know why my bibliography tool does not interpret this correctly. Okay, good. Okay, so let's go back to our discussion of the Langevin dynamic. So we try to follow now, I would not handle with the difficulty of epsilon going to zero limit. Actually, in this section, we keep both finite, and just remark that this equation, I think we have already remarked. So in the Gaussian case, somehow it's easy because you can diagonalize the measure. Let's say write a product of a Gaussian, and then for every Gaussian you have a dynamics which looks like this. Is the Oste-Uhlenbeck one-dimensional Oste-Uhlenbeck, and then you just write them all together in a linear way. Okay, so for the linear dynamics is not difficult because you can diagonalize the Laplacian, and then this become here you have an identity operator, so it's the identity. The Brownian motion remains independent when you diagonalize, and then you can just consider each Fourier mode, and they evolve independently. Okay, so you have only a one-dimensional problem. This is not, it technically is an SPD. Okay, it's not even SPD. It's just a system of finite dimensional system of SDs. Okay, and if you, we will, I will need to work a bit with stochastic calculus, but as soon as I can, I just get rid of stochastic calculus because we will not need it much. Okay, for the basic stuff we will not need it. So an exercise, if you feel it, is to check the invariance of mu under this dynamics. Okay, that is yeah. Okay, here it's trivial. Oh, okay, trivial. Here it's elementary because the measure it's Gaussian. This is a linear transformation of Gaussian, somehow the solution. And then you can prove that you say Gaussian, and you have just to check that the law at every time, it's the initial, okay? And I think I did it correctly now. I don't remember if this is the right normalization. I think it's correct, okay? To have the Gaussian free field you have to normalize in this way. If you don't normalize like this, there is a 2 appearing. Remember when we discussed the Oste-Uhlenbeck that we had the exponential of alpha, but in the denominator, the invariant measure was 1 divided 2 alpha. Okay, so if you don't keep track of the normalization, you don't get the measure right. Okay, so my goal is not, okay, that's first step. Then I want to construct dynamics which leave the measure nu invariant, okay? And as I wrote here, I will get rid of epsilon m in this section. Everything will just refer to the finite dimensional situation, okay? And okay, you can guess like in infinite dimension, or if you have some experience, you can hope, okay, let's hope that you can get away with just making a small change to this dynamics. Okay, so now I ignore every index, I ignore everything, and just write like this. But imagine this is a vector. Okay, so it's a vector, is a system of equations. This is a matrix, is this Laplacian. Again, okay, in infinitely many variable. I mean, not even infinite, it's a matrix, okay, in a finite dimensional vector space. And then we have to guess what we want to add to get the right thing, that is what I want to have, okay? I want to have that, well, see, so this is the initial so what was u? Okay, u of phi, let me copy so that I define what is u. So u is just this this exponent, okay? And I will write epsilon, but okay, we take it 1. Okay, so v is given, is a 4th order polynomial, and u is just this potential, okay? And I don't want to write the integral. It does not play any role at this point of the consideration, just a function. This is a function from R to the lambda to R. But lambda here, it's finite dimensional. So maybe let me be precise, okay? Okay, let me be more Bourbakist and just write in this way. Okay. Yeah. This is what I want to prove. Okay, you give me a function, then I want to prove that at the initial time I know the law. Okay, so I impose. I'm in a probability space where at the initial time I'm distributed like nu. And then I want to solve this this ODE or this SDE forward in time. And then once I have the solution, somehow I want to have the same, I want to have, x0, yeah. Okay, in this way, if I write in this way, let me say x0 distributed like mu, okay, because I put explicitly the reweighting here. And of course, the normalization is the same, it does not change, okay, because it stay the same. Okay, so this will be like the integral of f or phi with respect to nu phi, the phi, okay, which you can write just, but please ask question if you feel puzzled, because here I'm restarting from 0. So you have a chance if you get lost, because I made a lot of confusion. You have another chance here to not get lost again. Okay, so ask question. Here it's a finite dimensional integral. Yeah. No question. Yeah.
Sorry. In the right-hand side, it should be xt or x0.
No. Here is x0 because the only thing. So the measure. No, that's correct. So it's correct. So the measure, so somehow, let me think actually what I want from life. Yeah, so what is, the point is that what is this measure? Yeah, no, okay, the point is what is the process and what is the measure. So let me see if I wrote. Yeah, so the measure, okay, let me write. Then if we denote, so I was not precise, sorry, the law of X, so this is why you don't, of the solution. So now this is a solution, okay? Now we have to pay attention. Thanks for the question. The solution X of this equation with initial condition given by the measure and the initial condition independent. Yeah, I'm sorry for that.
Okay, thank you.
Yeah, now you agree, no? Now it's okay. So now you have this because then this is what provide, so let me explain again. So the density, so I think it's okay because somehow this is a representation of that. And then you want that this measure, that somehow this does not depend on time, even if you go forward, okay? But this is part somehow of the measure, okay? I want this anyway, okay? So I could have said, actually, I could have written more. I could have said that x0 is just distributed like nu, okay? And then, okay, let me say note that under the measure, so under the measure Q, which is defined, the Q, this is on the path space, okay? Q dx equal, so yeah, but I think, yeah, I was a bit confused myself, so thanks for the question. The process X is still solution to the equation. And so this is just a way to the right way and the right way for us to get this, okay? And the initial condition is distributed like 0, and then you have, and this is like, okay, I could have defined this before, but okay, let's say I just wrote it. Okay, so we have this measure. Let me not call it, let me call it PV maybe, because I'm not sure if I want to use, okay, or P, yeah, maybe PU. It's the same, U and V are of course the same data, okay, they contain the same information. Okay, so this is really the measure PU, okay, and okay. So this measure is still not defined, okay? I have to decide what to put here, okay? But my goal is I want to put something here which keeps this formula the same for all times, okay? And you cannot put anything there, but somehow this will be my way to compute a stochastic quantization to introduce. Now that's the only point where I need somehow a sophisticated result for maybe, okay, people in stochastic analysis, they know, so I need to use this kind of formula because somehow I want to go back to the measure, to the law of, yeah, let me, yeah, I want to go back to the, yeah, actually it's not, yeah, I just noted that my notation is a bit, it's not very nice. Let me think what I want to do really. Okay, let me write in this way. Okay, so now I don't want to spend, yeah, because I got always confused by Gaussian, so I have to think 2 hours every time I apply it. And apply often, so it's something in my brain which is not working. So Gaussian formula tells you the following. So if you are not familiar with stochastic analysis, I think this part will not tell you much, but somehow I just need to find a reason what to put here, okay, to get this property. So I need to do a computation, and you can do in many ways. You can use semigroup. You can use the fact that you can, you could think of it as a Markov process and then guess what should be, but somehow that the way I want to do here. So Gaussian formula, so I can ignore the normalization, okay? It's not playing any role in getting these two things equal. So let me just look at the formula, which is very interesting because Summa normalization is the most difficult thing to compute in these formulas, okay? Actually, if you know the normalization, you know everything more or less, if you are able to compute the normalization. So in this formula, you don't need, somehow F will not look at the normalization. But you still need, so let me use the Gaussian formula we have for two test functions. So I need two test functions because I need to do something later. F and G, so you have two test functions, and then you compute something at the beginning, you compute something at the end, you have this measure, which I want to have here. And somehow I need to prove that this is independent of T. And now there is a formula which allows me to write in this way, where where there is a measure Q, so there are two things I have to define, where under Q the process X satisfy the linear SDE. So under the measure Q, you have so the process is the same. Okay, you can think about it as the canonical process in this space. Okay, there is only this process, but somehow, of course, there is something else around. Okay, you have this Brownian motion. Now you can change your measure in such a way that the Brownian motion become another Brownian motion. So where tilde B is a Brownian motion under Q. Okay. And somehow you don't have the drift anymore here. Okay, the drift has been absorbed here. Let me call it W because I don't want to put tilde everywhere. So let me call it W. Okay. So there is a new process W. It's not so we had already a Brownian motion. Okay, this Brownian motion is just this process minus these two parts. It's a Brownian motion. And then you can change measure, and now this part minus this part is another Brownian motion. But you have to put a weight which depends on your trajectory. Okay. I can even maybe make it larger because maybe it's getting too small. Okay, so this factor is there, and this is so this is a stochastic integral. That's fine. A stochastic integral with respect to a Brownian motion, and then you have a part which looks like this. So this is the change you have to make to the measure, and this is just this weighting factor. Okay, so now, so if you use Ito formula, so now this is the first non-trivial fact I need to use. So I know that maybe some of you are not familiar with Gaussian formula, but somehow is a way to write solution to some SDEs. So I want to, sorry, I go back. I want to write the law of this SDE, P, okay, as the law of this SDE, Q. But of course I have to change something, and I write a density, okay? And then the density depends on the part which is not anymore in the equation, okay? It depends on F and on this Brownian motion. But now you can use Ito formula. So now I want to look better at this part. So I can use Ito formula apply to this function, okay? U of xt, then maybe you know Ito formula, maybe you don't know, but essentially you get something like this, U x0. So Ito formula is like the fundamental theorem of calculus, okay? You write, okay, how this change in time? Well, it is initial value plus what is the change in the x and the gradient. So this is the gradient of this object. So let's write like this, not to confound with the finite dimensional gradient. Actually, yeah, with the Laplacian in the set. Okay, so This is second derivative. So the formula tells you something like this. Now, I don't want to be too precise, but okay, so I tell you, this is the trace of that. Okay, you can write down the details. There is no 1/2 because I have 2 here. So if I make it correctly, there is no 1/2 here. Okay, this is the quadratic variation of this process. So anyway, there is a formula like this and looks like the fundamental theorem of calculus, but you have a correction term because this object is not differentiable. Okay, so you get a term which is the increment of x squared, which is like the increment of w squared, which is like t. That's all you have to know at this level. Believe me that you have a formula like this if it's regular enough. And then you say, okay, but what is x? And I write x under the measure q, and it looks like, sorry, I call it, yeah. It looks like this, okay? dx, okay, you can read it here, okay, is a plus dw, okay? So I wrote dw and then I put, okay, here I wanted to change notation and let me put a of x, okay? This was what was a, but I don't really need to know very precisely. And let me give a name to all these quantities like this. Okay, so you have a formula like this. Why I worked so hard? Because then I have an object where here I have a Brownian motion, and this is a stochastic integral. So this is exactly, so it looks like this one. Okay, so what I'm trying to do, so I can rewrite the above formula. We can rewrite, we can rewrite this. Let me give a name. Equation Girsanov, yeah. As not, yeah, you could rewrite like this, but it's not very useful. But I can rewrite in this way. Okay, I have G and F. I don't touch them. I don't touch the. I made a mistake. Did I make a mistake? Yeah, here I make a mistake. Okay, this was my mistake. Sorry, I don't really. Sorry a moment, there should be a problem in my formula. Yeah, here I always make a mistake, and I think I did it again. Let me say, okay, so, yeah, okay, let me, I don't want, okay, let me write like this, okay? Now, somehow you see, yeah, okay, let me write everything, sorry. I have something like this. So I want to take half of this and rewrite using this formula. Okay, so what you get half of ux, and then you subtract, of course, you add this stochastic integral, for example. You add this stochastic integral, so you subtract this stochastic integral, sorry, this one, half of that actually. So that's what was perplexing to me. And then you subtract half of q and you add, yeah, and you have half of f. So this is fs. And then you subtract half of q. So I think the formula looks like this. Okay. And then take, now somehow this suggests you a choice, which is not obvious that it's the right one, but you see from here that here you can cancel these two terms. If you take fs to be, I have a problem with the sign. I know that the sign for me is not very, So let me see. This is is minus U0. So so minus U0 I can take on the other side. So it's actually taken with plus here. And here I have with plus. Okay, so I think it's okay. And I need to take Fs equal to minus. Yeah, I have this one alpha round, which I don't like, but okay, let's write it down. Probably it's correct. Okay, to cancel the stochastic integral in the exponent. I don't like this stochastic integral in the exponent. Okay, is Q equal P of U? Good question. I asked it myself. No, I don't think so. Okay, let me finish and we discuss, because now, I mean, yeah, it's a good question and I could ask it myself and I would not know the answer. So we can think about it later. So why I wanted to do so, okay, to get, so where I want to arrive. So I want to arrive in so all these cancel and you have this formula. Now what is nice about this, actually I can write more explicitly. Okay, now you have du xs here and you have 1/4. Okay, so what is nice about this formula, to which I don't trust the coefficients, but somehow I don't care about exact coefficients at this point. The only thing I care is that, you see, looks like it's something which is symmetric with respect to time inversion. Okay, remember, for example, the argument we had in discrete time, in the like finite dimensional case. Okay. And since Q is reflection invariant with respect to, yeah, is time reflection invariant because under Q, the process X is just an Oste-Uhlenbeck process, a stationary Oste-Uhlenbeck process. Okay? Think about it. This was all we had. Okay, let me say, maybe note that x0 is mu. Okay, so this didn't change it because x0 is independent of the Brownian motion. So the Gaussian transformation will not affect x0 in some sense if you do this. And so this is under Q, X is an Oste-Uhlenbeck stationary process. Okay, so it has a law which is time reversal invariant. So here I can use this fact. Okay, now you see everything, it's time reversal invariant, but not this. Somehow this choice of drift make my initial problem time reversal invariant. Okay, and then I can use and then we can rewrite this. We can rewrite this as how we can rewrite this. Yeah, you can exchange the two functions. You agree? Let me copy because I'm not sure that it's the coefficients are the same. Well, we exchange it, the two functions. Okay, easy. If everything is well defined, but okay, this depends on condition and the coefficient. Okay, you can check that things are right or take bounded coefficient. That's fine for the moment. Now taking, what happens if you take f equal 1? So now if you take f equal 1, if you take f equal 1, sorry, what I want to say. No, I copied the, sorry, I copied the wrong conclusion, sorry. I need to do 2 steps. So the first step, if you take f equal 1, then there is no f here. So I just copied the same, this is really the same formula, okay? You don't need to know what is this as soon as is invariant under rotation and under time reflections. So you can exchange it, okay? You can look from 0 to t, it's the same as looking from t to 0. And then, so essentially, yeah, you can exchange the functions. Then you take one function equal to 1, then you get this. And what was this? Well, you look back what I was computing. Well, I was computing this quantity, okay? So you have this. So you see that this expression does not depend on t, okay? Because it's equal to something which does not depend on t. Good. And now you take on the other direction, you take g equal 1, and then you have this here. Let me see. If you take g equal 1, yeah, I wanted to compute this, okay, but I learned what is this? You look, what was this? Well, this was that, and now this expression is exactly like this, so it has to be equal to that, okay? You put together all you know and you get this, and you found what you that is what we were looking for. Okay, so the first equality is the fact when we have exchanged half of this with half of the other rest of the formula and the Girsanov formula. So we went from exponential to q. And then you check this formula and you see that this is equal to that. So you can take just f equal to g here and take g equal to f, and then you get that. And you are done, okay? So we can choose fs. So, okay, let me maybe resume the thing. Okay, all these provide, yeah, okay, okay. All this is okay, provided we can perform all these computations, okay? And then what is the only problem we had in this computation is the integrability, the fact that you can perform this kind of transformation, and essentially is the integrability of these exponentials, okay? You can reason by approximation, actually, in the sense that you can perform Girsanov theorem with a bounded potential and then take the limit. So really you need only this object to have some integrability. So you can ask for u, for example, to be bounded below, and all this quantity, which is the quantity appearing here. So let me maybe, I'm not sure of all these coefficients. They look strange, but okay, let's trust that they are the right ones. This object was something like this is like the trace of the second derivative. This was some gradient and this is like the gradient acting on this vector, and here you have the gradient square. So this is finite dimensional operations, okay? You are in this Euclidean space, and these are just the gradient and the derivative and the Laplacian in this Euclidean space, okay? And okay, if this function satisfies this for some t, then this is enough for do it for some small time, and then for all time.
Sir, I didn't understand where we use the equation we got from taking f equal to 1.
Yeah. Sorry. Yeah. So okay, in this expression, I think okay, maybe there is another way, but this is the only way I know. And I was able to explain. So I take f equal to 1, okay? In this, so I get this, okay? That's okay for you? this formula, yeah. Then here, so first of all, I look at this formula. So this formula, you look here, and you know that correspond to that. And now you see that this is equal to that, provided f, you put f here. But if you put f here, you have to put f here, okay?
I see. You take G equal to F.
Yeah, I take G equal to E, okay?
So
taking G equal to F in the previous formula, in the previous formula. Okay. Okay, and then you get that, okay? But you need both because you need to do this two-step reasoning, okay? But it's based on, so what is telling this computation is that this process is time reversal invariant, okay? And then, okay, this is just, let me make a remark because maybe many of you don't care about this remark, but somehow it's, you need to pay attention to make it carefully, otherwise, especially if the coefficients are bounded, like all the derivative of u are bounded, that's fine, but then we need polynomial interaction. So you need to justify in the limit and you need to do some argument. So what we learned, so we learned something. So, so the solution of this equation, now I have this 1/2 more. I would like to ignore it, but okay, let's keep it there. I was hoping that this would arrange that, but apparently not. Leaves this measure invariant, okay? Provided U is nice enough that all this computation makes sense. Okay, so that's my Langevin dynamics. Okay, that's how you justify this defect. So we will take this equation as stochastic quantization. Note that the process X is time reversal invariant. Okay. We essentially gave a proof, okay? Give a proof of this above. You can fill in the details. It's not very easy, but it's not very difficult. Maybe think about it if you want to think about it. I can leave it as an exercise, okay? If you want to understand a bit better what's going on, maybe you should try to do it. Provided, let's say, assuming everything is integrable and you have all the integrability you need, like you bounded with all the bounded derivative.
Excuse me, the condition on the remark, is something similar to the Novikov condition when we are dealing with the measure?
You need Novikov condition to go. Usually, Novikov condition you need to do the Girsanov transformation.
Yeah, exactly.
But yeah, so a priori, I mean, if you just proceed, when I do it in the course, I do like this. But okay, then you look better somehow if you can go around because you can. Okay, this is technical. Okay, so first order answer is yes. Okay, it's a Novikov condition, but it's we are in a better situation because our choice made the stochastic integral disappear. And Novikov condition, it's really something about the stochastic integral, okay? It's the difficulty of doing the Gaussian transformation is because you have to bound the exponential of the stochastic integral. And so since it disappeared, somehow you don't need to care anymore about Novikov condition, provided of course, you have to do Gaussian transformation at some point, but you can imagine that I do on approximation where I know that I can do because Novikov condition satisfied, and then I don't. I mean, why I'm so worried about all this because okay, let me make a point because maybe clarify the situation. Okay, what you want to do is that you want to apply this to this potential. Okay. So you have to think, and now if you start to think to this potential, it's not obvious anymore, okay? Gradient of u is like phi cube. Novikov condition is not so good for you, okay? Because Novikov condition does not see if here you have a positive or negative sign, okay? So you have to be careful. That's why I'm being quite careful when I pronounce it, because it's not so obvious when you want to do for unbounded coefficients, okay? So I think let me think what I want to say now. Okay, so what happens for unbounded coefficient? You see, this is, you have to do something. Okay, I don't want to insist very much, but it's not trivial to justify all this, because this will be like cubic power 6, and this will be like power 4. Okay, but you have this power 6, and I don't remember. I think here the sign of this is correct, so that's fine. You have to be careful, and you have to use somehow more properties, okay? That's why, and surely the Novikov condition is not holding here, okay, if you just proceed directly using the Novikov condition, okay? Because, for example, okay, if I go back, you see f is the gradient, will be the gradient of u, which is cubic. So if you try to prove the Novikov condition, you have the exponential of a cubic, of a power 6 of a Gaussian, which there is no chance it exists, okay? So you have to be a bit careful about here. You cannot use Novikov condition, but you don't need at the end, because there is no stochastic integral in this expression. So here you just to prove that this is okay. And here you see this term is helping you because it's negative. This term does not have a sign, but you have to pay attention, and these other two terms helps you, okay? So at this level, it's not difficult to do the thing in this particular example, for example, okay? But this is really technical, okay? Just message, one has to be careful, okay? That's why I'm insisting on this point. Is okay, my explanation?
Yeah, of course.
Okay, yeah. No, don't hesitate to ask again. So we have, this potential, so that's why I need a lecture to discuss this equation, okay? Because it's a finite dimensional SDE, but it contains some difficulties which are non-trivial somehow, okay? They are not much very difficult, okay? You can solve at the master level, let's say, but still, okay, you have to think, and it's important for us to understand the structure of this equation in our particular case, okay? So from now on, I fix myself on this case because this is the case I'm interested in. And you have two orders of problems with such potential, okay? The first one is the gradient. So now I compute the gradient in a given point. So this is the derivative just with respect to this coordinate, and you get this, okay? So this would be like the vector field sorry, this derivative is really that one, okay? So this would be like this vector field appearing here, okay? And you see that it's polynomial, okay? So it's not globally Lipschitz. Sorry, let me go back to see if my notations are consistent. I think yes. So this is not globally Lipschitz, and first of all, the solution of the SDE could explode in finite time, okay? Because even the ODE could explode in finite time. Okay, now of course, I mean, if you just use the basic theory, you have to use more properties of this equation, okay? Okay, then, so once we solve this problem, we have to worry about invariance, okay? So time translation, time invariance, and sorry, about invariance in the sense that about making rigorous the above proof, okay? Fixing the details of the argument above. Okay, so invariance, I mean invariance, I mean that if I start from the measure nu, I want that the low at every time is the measure nu. Okay, about invariant of the measure nu with respect on this dynamic. Okay, so this problem, this second problem, one is essentially technical. Okay, in the sense that okay, you have to worry about some details, but there is nothing seriously dangerous there. Okay, that's however, for us it's more important to have global Lipschitz solution for this equation from the equation. Okay, you could use the fact that the measure it's invariant to deduce that the solution does not explode, but I don't want to do this. Okay, one could use the measure nu to conclude that solutions of the SD do not explode. Okay, that's a way to do, but we will not do it here. Again, because I want to understand better the equation in itself. I don't want any help from the measure. Okay, I want to understand. So you see, the point of view of these lectures is that I want the equation to tell me something about the measure. I don't want to use the measure to understand the equation. And this has some advantage later on, okay? You could use the fact that you know the measure to discuss the invariance of the equation at this level, but somehow it's useful for me that we start to know better this equation, okay? And what is, so yeah, so let me say first attempt. Okay, first method, let's say first method for non-explosion. So first method is one could use, but we will not do it here. Okay, I just second method, which we will not use either, but so that you see that there are many methods, and actually all of them have sometimes have advantage. Actually, most of the time I have advantage of what I'm going to do, but not for the problem I'm looking at. Okay, later on. So a direct approach, you test the equation with the process. Okay, so what you want to do is that you take the scalar product of this equation with the process and you use it to form. Okay, sorry. So you write something like this. Okay, so you recall that this is just a bunch of variable indexed by x. So you try to compute it to formula. And of course, I got it wrong because maybe I need 1/2 here. Don't trust my coefficients, okay? And then you use Ito formula, okay? And Ito formula tells you two things, okay? You use by Ito formula. Okay, is the increment of that, and then you get the quadratic variation. The quadratic variation are Brownian motion in any position, and then so is this still a sum? Okay, you have a sum of 1 because you get quadratic variation dt at any point, and then you don't have 1/2 because there is this 2 around. Okay, so Ito formula allows you to write this, and what is the advantage to write this is that, okay, this looks like, now you expand what is the dynamics of x, and this was like linear part, and then you have this vector field. Again, okay, now I screwed up all my normalizations. And then you have the Brownian part, so this is part of this stochastic integral, and then you have this dt, okay? And you can write this in this way. Okay, now you give a look, there is a sum. So why a sum? Why I insist I want to sum? Because if you sum over all positions, then you can integrate by part the Laplacian here, and you can write this as a positive quantity. So you see why this is interesting, because yeah, this give you, when you compute everything, this give you really a second order, this give you this polynomial, this maybe remainder term. So I put in G everything that it's positive. Integrating by parts the Laplacian. or maybe summing by parts. You get that, okay? And then you get this term quadratic, and then you get this stochastic integral, and then you get this constant term. And now you see that this give you a priori estimate. There are like 10 ways to estimate this. For example, this term, of course, you can use Gromwall, okay? This is positive, you can ignore. And here you can use Gromwall inequality. So the case you don't like is when beta is negative, because when beta is negative, this is, when beta is positive, this is growing. This is stochastic, so if you take an average, this disappears. Okay, so let me say in this way, okay. For example, if you take the average, then the stochastic integral disappear and you get a formula like this. Okay. And then from here is not difficult to conclude by Gromwall, okay? Because you see you have, yeah, I've integrated in time, okay? So you get a formula like this. There is a beta in front, but you recognize that here you have the same, okay, let me write in this way. Here you have the same quantity here and there, so you can use Gromwall, or actually you can reabsorb this in this term. You can do many things, but we are not going to do anything because I don't like to take this average here. Okay, so somehow the fact that there were stochastic integral force us to take an average. And okay, here it's easy and you can imagine you can do other things, but in further context is not very useful. It's not very easy to use this approach. Okay, so this is our second method, and our third and last method, which is the one which will be used, okay? But this is not robust enough for what is going on next week. Okay, so we will not use it because it will not work. And somehow, yeah, this is also part of the idea. So these are the standard techniques, okay? When I teach SDs to master student, I teach Lyapunov functions, or I teach like this kind of argument with invariants, okay, to globalize a solution which could explode. So this is essentially a Lyapunov function method, okay? You from that you can also derive the fact that the measure never, there is no explosion time, okay? The explosion time is plus infinity, and this solution lives for every time. But I need more information for the problem at hand, and so the last method, which looks again strange, but somehow is the method that go farther, has more latitude in this business, okay? And actually it's more elementary in the sense that you will not use Ito formula, okay? So if you don't understand Ito formula, don't care, because we have a more useful, goes as follows, okay? This is essentially what is called the Prato, if you call the Bush. Okay, Arnaud will kill me because I think I misspell his name. Okay, so okay, in this context is overkill to call it the Prato de Bush trick, but the idea is that, and you write the solution. So you split your object. This will be useful, very useful next week. So you split your object into parts, y and z, okay? And y is the solution of the linear equation. And z is what remains, okay? Z is x minus y. And z is what remains. Okay, so I think this is an important point. So, yeah, Anoste-Uhlenbeck. Yeah, so you know y very well, okay? Anoste-Uhlenbeck process, okay? Z is what remains, okay? You have a solution to your SD, you have the Gaussian process, and you write this as a difference. I skip what initial condition you want to choose because we will discuss this later. Okay, so what is the question for Z? Okay, now you look a bit. Okay, they are not. I should say they are not stochastic differential equation. Okay, because there is no stochastic integral in the equation. You can write, if you write the integral formulation, it's really an equation which makes sense for any continuous function. Okay, but when you take the difference, it's even better because the difference solve an ODE. Okay, so this you consider the difference, you do your computation, and you realize that there is no stochastic integral, so actually you can divide, maybe not like this, but you can divide by t. Okay, it's an ODE now. So I think this is a finite dimensional ODE now. So we are even in a more elementary context. And of course, it's a random, okay? It's a random ODE because y is coming from outside, is generated by the noise. If you can imagine that y is the noise, okay? You just change it variable so that the noise appears in a nicer way. So you are injecting noise in this dynamical system, and then this dynamical system evolve in this way, okay? It's not autonomous, but it's not, yeah. Okay, so this is like a random dynamical system now. Okay, smooth in the sense that evolution time is nice. Okay, now I can do the same trick again, but even more elementary. Okay, now it's like in PDE theory. Okay, imagine this is like a parabolic equation now. Okay, you have a Laplacian, and this what we will do next week to handle this problem is look at as a PDE with random coefficients, like this one. Okay, and then what you do, well, you test with Z, and now you can do the computation even if above before you couldn't, because now you can use just you don't need Ito form. Okay, you just test, and that write Z times the derivative of Z as the derivative. Of course, I'm not able to do it because 1/2 and all this stuff. So let me maybe put on 2 lines because it's too much. Okay, you have just the same computation as above. That's an exercise. I did it for you here. And you have G as above, because somehow this is the part of the drift. So there is the linear part, a quadratic part in Z, and then a fourth order part in Z, and then you have a lot of correction term because you have to expand the binomial here. And it looks like this, okay? There is certainly a term cubic in Z. There is a term, yeah, cubic in Y, and then there is a cross term here, and then you have some linear terms. I hope I put everything there. And here, everything depends on lambda, which was the constant in the quadratic. It's important for us, okay? That's why I insist on this context. Lambda is positive. Lambda is also inside G, okay? So is this okay for everybody? Because now it's done. Okay, once we have this, remember that our problem is that the dynamics could explode, but you see from here that the dynamics does not explode because somehow, you see in the right hand side you have norms in this finite set, but these are like Lebesgue, very easy Lebesgue spaces, okay, discrete Lebesgue spaces. So you can yeah, let me rewrite what is G. Okay, so G was this. Okay, okay, maybe I will not rewrite, but let me write in this way. Okay, where G. So let me, instead of just repeating the formula, let me write in a more interesting way. So this is nabla phi. So you start to see. Okay, this is finite norm. Okay, these are A2 norm. Then you have m squared, because now we have to do some estimates. So we need to understand the analytic structure of this problem. So here you have still an L2 norm, sorry. And then you have lambda and L4 norm. Okay, this will be very important next week, but let's, okay, so we have this, okay. With the natural Lebesgue spaces on lambda, okay, with counting measure. Okay, so lambda, remember, is lambda epsilon m. Okay, it's a finite set. But okay, at this point, you don't care anymore. Okay, these things make sense even for infinite sets, but of course, would not work so easily. Anyway, okay, so now what is the game to play? You see, you have this quantity. So this is the increasing time of the L2 norm. Okay, and then you have these quantities on the right-hand side. So they are helping you because they are positive. So if you put on the left-hand side, they push down the L2 norm. Okay, so they are nice things. And now you have the bad things, which are the things for which you don't control the sign, because remember that y is just a Gaussian process, so it can be positive and negative. Maybe the only term which is nice enough is this one. I think we have a minus here. So this term is still nice, you could put on the other side, but we don't know how to use it, so we put it there. But surely you have terms which are not good, and you want to bound. And I'm using this approach because later on there will be more terms, but somehow the general picture will be the same. Okay, so maybe here you can do other things, but this will not be true anymore at the end of the day. So really the idea which works is I have these good terms and I have the bad terms, and I want to control the bad terms with the good terms. Okay, so this I will never need to use because this is somehow statement of regularity, even if in discrete space. But I can use this, okay, because these two objects control the growth of the solution. So you see here, this could become very large and you don't want it. So what you want to say is, sorry, so what I want to say, yeah, sorry, I got, yeah, I think I'm here, good. And then the idea, okay, here you have to do some computation, but I think the idea is quite straightforward, okay? The idea is that you bound everything on the right-hand side. You can use the L4 norm of y. You can use the L4 norm of z, which is inside here, with a small constant. Okay, you have to use Young inequality, but you see, because any of these objects you can bound by the L4 norm plus the L4 norm. Okay, by homogeneity. Yeah. Okay, because they are like products, and then this is the L1 norm of all these, and then you use Holder inequality and then Young to separate this, and you can put a small constant here, and you have to put a large constant there, but you don't care. And the idea is that now this term can be eaten by that one, so you take a small constant, delta, and you conclude, this is the idea, okay? Maybe it's, I think it's not, I mean, it's not so difficult. Okay, it's very elementary actually, but that's the idea. Okay, then if you use this idea, so you can just get rid of this because you can eat it with that. You have this term, but okay, this term is okay because that's the other process, is not the solution Z you try to control. Okay, why is this Gaussian process, and you know everything about it. In particular, you know that the L4 norm is finite and it's continuous in time, so you can write this formula, okay? And this tells you many things about Z, provided you know Z0. Okay, and in particular, this tells you that the solution cannot explode, okay? And you have even an explicit bound on its growth in terms of Y and Z0, okay? Which is not so nice, okay? In the sense, okay. Okay, that's a point. Okay, that's one of the key techniques we will use next week, and it will get a bit more complicated because there will be like more terms, but the idea is the same. Okay, there will be the good guys and the bad guys, and you just cross your finger and hope that all the bad guys are killed by the good guys. Okay, and then everything ends in the best way. But the good guys are good, but not so good. Okay, why it's good? Because I know him. I know that it's not going to play any trick on me. Okay, why is a Gaussian process? Okay, of the two, we know very well. Well, why it is the U process. It is Gaussian. I know everything. I can compute everything you want to compute. I know how to compute it. Okay, I want to. So that's not a problem. Okay, that's my process. On the other hand, I do not know so well Z0. Okay, because Z0 is distributed like, okay, here it depends what you want to do. Okay. Z0, because Z0, what it is, okay, is X0 minus Y0. Now it depends how you choose the initial condition of Y0, because it depends. Okay, this you can make various choices, but the natural choice is that you want Y to be stationary. So this is really the difference between nu and mu. Okay, in the sense that this is distributed like a difference of a random variable. Okay, let me put it, yeah, a random variable with this law and this other law. So, but of course it's not correct like this. So let me just write in brackets, oh, yeah. Nu minus mu, just to say that it's informal. Okay, it's the difference of two random variables. Okay, because we do not really know very well nu. Okay, is actually the object we want to study. I can write it down, but the point, for example, we do not know uniform estimates, uniform in epsilon and m, for example. Okay, in this sense, I don't know it well. For the Euler-Uhlenbeck process, I know everything. I know that it converges when epsilon and m is going to infinity, no problem. I can compute things. For the initial condition, I don't know. Okay, so this initial condition, I don't know it very well in some sense, because as soon as I start to look at the limit, m going to infinity or epsilon going to 0, then I lose control of this. And if I lose control of this, I lost control of everything. Okay, it's not point. So somehow this strategy always, you can do it up to here, but then you need to introduce other things in the business. Okay, and for example, in the first works that were using this for stochastic quantization, they always used the measure, the invariant measure. So some information about 543 to control this term. So which was not very satisfactory, because if you have to use the object you want to construct in order to proceed, then maybe it's not really in the spirit of stochastic quantization. Okay, the initial spirit was really, you want a way to construct the invariant measure via this more complicated dynamical process. Okay, so you have to get rid really of this. You have to do something for this dependence, and there are various solutions. Okay, so what we can, but we can do it in many ways. One way is to remark that not the following. So even if x is stationary and y is stationary. So let me, yeah, because we take x. So now there is a problem. Okay, let's see the structure of this thing. Okay, you take x0 distributed like this, and you take epsilon0 distributed like mu. Then okay, you can do like this, and then these two are stationary, but they are not independent, of course. And more importantly, Z is not stationary. Okay, so what you don't know in this business, okay, you can start how you want, okay, but somehow X and Y, they proceed together, and they are driven by the same Brownian motion. Okay, and we proved that X is stationary and Y is stationary, but somehow their correlation depend on time. So the marginals are stationary, but the joint law, the coupling depend on time, because there is no reason why not. And so Z depend on time. Okay, you can even see very well from this equation, there is no reason why the law of this equation has to be stationary in general. So you need to prove, one would like that there exists a coupling, for example, okay, of x0 and y0. So what is a coupling? Okay, so you find a joint law. Okay, you want a joint law for x0 and y0 with marginals nu and mu respectively. Okay, so this is a coupling. It's a joint law of the two random variable, which has the two projection as you want, but somehow which are non-trivial correlation, so that the process xy is stationary as a pair. Okay, that is when you look at them together, they have stationary, in particular they have stationary dependence one of each other, from which would follow that Z is stationary. Okay. Why I'm interested in the fact that Z is stationary? Okay, that's just to remark that in general is not stationary. You can, okay, there are various ways to, okay, now let me see what I want to do now. If you have question, it's the right moment, because I have to think maybe 2 minutes, 1 minute. Yeah, there are various things one can do at this level. Okay, are there any questions, remarks? It's fine, or I lost everybody. You have to tell me if I'm going too fast, or maybe if you think something is important but you didn't understand, then maybe I can tell you it's not important, or I can tell you no, it's important, and I will be better to explain more deeply. Maybe while you think, let me give a plan for the last half hour and what I want to do in this case. So this is the starting point, okay? And I showed you here how, so we set up the stochastic quantization of the model in the way I want to explore, that is this parabolic equation. And we started to get property, okay? We found stationarity, which is the basic property, okay? You want that somehow you can represent the law. Yeah, maybe this I want to say, okay? So far, so what we have so far, okay? So far, maybe let me say, okay, now we have a good dynamics. Yeah, okay, and we have good bounds, okay, and then in any case, so let me make this remark. In any case, so so far we have invariance and the fact that the dynamic exists for all times, and we have even this uniform bound. Yeah, you can use both equations. Both equations say the same thing essentially. So let me label equation a priori discrete. So in any case, what we have so far is that so for any test function, now what you know is that, so now you have this, okay? So we have achieved that for any test function, we can write this as the expectation of f of z, okay? Or even for any t, okay? For any f and any t, we have this, but actually we have even more, okay? You have that you can take the integral, sorry, not z, x, okay? But x now for us is just y plus z, okay? And here actually you can take an integral because it's stationary, so that's exactly everything, it's the same expression, okay? So this is the stochastic quantization equation, okay? In the sense that you, okay, one version, okay, that's the easy version. There is a more complicated one where you have also ergodicity and then you can remove this expectation, but you need to take the limit, okay? But you see, you have represented this is what I promised, okay? Represented the measure as the integral over the push forward of some Gaussian measure, okay? Here we really think estimates on x are given via y and z, okay? So you could even write this as y and z, okay? Because this is what will be useful later, okay? Y, you know it very well, is a Gaussian process. Z is something which depends on y, and somehow which correct the Gaussian process to give you really this law, okay? But somehow you have this. So this is maybe my friend, maybe let's put it in a box to make it more prominent. Okay, so this is key point now. First thing we can do, I wrote in my notes, is that so now let's construct, just to get some more from it, let's construct a stationary coupling, okay? Y and Z. Okay, so what does it mean? Well, I wanted a joint law which is stationary, okay? And how you do this, here it's very easy, but I think if you've never seen it, it looks interesting. One uses Krylov-Bogolyubov, okay? Argument. Okay, what is Krylov-Bogolyubov? Well, is this idea, okay? We can construct, so this is, okay, we can construct a measure on the pair of fields in this way, okay? So I define a new measure, gamma of t, by taking these kind of averages here, but not a function of the sum, a function for any bounded function f of the pair phi MC, okay? And remember that this is, where is this pair? So this pair is just function on n lambda and then function on n lambda. Okay? So this is very, and the law, it's a law on the pair of fields, okay? So this is a coupling of the two random variables, and you construct by coupling the two processes, where y and z are started, okay, as above. Okay, I mean, you y started from mu, that is y0 is distributed like mu. So this is very, how you would do in a computer. So you extract y0, you simulate y0, then you simulate x0. So z0 is just the difference then. And then you start your two processes with the same Brownian motion. So they produce correlation among them because they are driven by the same noise. And then you compute this average, okay? This gives you a measure on the pair, because somehow you take the empirical measure of these two processes. And then, okay, what you do, so this is not time invariant, okay? But essentially what you want to do here is want to take the limit t goes to infinity, okay? So you have that, so we need to check that somehow this family of measure it's tight. Okay, we have a family of measure that could just run off to infinity. So we want to be sure that they remain in a compact region. And actually, so you try to compute, for example, the average of this function, which is very nice because it grows. So it has compact level sets in this space. And okay, you use the definition, then you use our bounds, and you get this estimate. Okay, because the integral of g, I'm going back to my uniform. Okay, the integral of g is bounded by z0 and the integral of y. Okay, so essentially you get twice the same quantity. Actually, you see, this is a number. Okay, I told you a priori you don't know it, but here you don't care because there is t. And so when you send t to infinity, this is going to 0. The other quantity, it's stationary. So actually, okay, y is stationary. So here I can even simplify because this integral just make t. So essentially this quantity is twice that and twice this thing in 0. Nothing more, but without t. Okay, so this is important. There is a t here. And this t, and actually, yeah, okay, it converges something which does not depend on t, okay? But okay, at this point, I don't want to remark it. I think in other argument, it's important that you have this t. Actually, next week, it would be important that you have this t because then you can make this small. Because remember, okay, this was my argument before. This you don't know very well, okay? So this can be made small by choosing t large, provided it's finite, okay? And this quantity does not depend, okay? So you can send t to infinity. Yeah, okay, I think I don't want to say anymore here. Actually, so I just showed to you that it's uniformity, okay? So it's no point to, which is uniformly bounded in T. Okay, so you have this family is uniformly bounded. Yeah, this implies that the family gamma t is tight in blah, okay, in this space on, and one can extract a weakly convergent subsequent to a limit gamma, okay? Let's call it the limit gamma, okay? And then, okay, so what happens also, note also that if you take a function which depends on the sum, then of course you already know what's going on, okay? It's the measure nu, as we said before, okay? It's this measure, if you take a function of the sum. Therefore, the law of the sum under T gamma is always given for any T. As a consequence, the law of phi plus psi under gamma is no. Okay, so under the limit we have found. Okay, exercise for you if you want to understand better is to prove measure gamma is stationary under the joint dynamics of y and z. What was the second variable z? Not z and y. Okay, so meaning that if you start, okay, yeah, if we start, yeah, okay, let me say in a way that, under, yeah, actually, with the Krylov-Bogolyubov, you can construct a stationary coupling of the two processes. It's easier than to prove this, okay? Okay, let not me give hints, just try to prove something. It depends how you formulate. Maybe it could be easier or more complicated. So try to think if you want. But somehow that is true. Prove it. What? Prove what? Prove that the measure mu is stationary under the joint dynamics. Okay. For if yeah, I'm a bit sloppy here, but there is a way of interpreting what I'm saying, which is true. Okay, so that then the pair is like this at all time. Okay, essentially because here you already took a limit, so this is invariant under times translation. Okay, I think it's even prove it also. Try to understand if the dynamics, I'm not sure if it's reflection invariant, okay, of the pair is time symmetric. This I'm not sure, okay, I'm not sure. Okay, I'm not sure does not mean it's false, just right now I could not say. I would have to think about it. Okay, so this is, well, okay, we have a stationary coupling of Z and Y, which gives you the for representation of the process. And moreover, at having given time is given by this coupling. Okay, so I don't have much time. I think we did. I had the impression to go too slowly, but maybe you can tell me, okay? I always the impression to go too slowly and then people get lost. So I think yeah.
Yeah, I have a question.
Sure.
I might be confused, I'm not sure. So here it's all finite, so finite epsilon and finite m.
Yeah.
But in the case of, I mean, if you want to get uniform estimates in epsilon and m, you've got to take capital T to infinity.
Yeah, so here it's not so, yeah, thanks for the question. I think it allows me maybe to discuss this point right now. So what happens if you want, I wanted to take m to infinity, okay? Here, that is the next step. So here you could almost, the problem is that this is going to infinity, you cannot just take, because this is just the L4 norm of a process which is stationary in space. So in every point of space is the same, this is going to infinity. So this bound will not help you. Sorry, let me go back to my initial bound, okay? Let me go back to, yeah, let me go back to this bound. So, okay, so yeah, so this is the continuation. So I'm not sure if you had a question, but the idea is that now I do the infinite volume limit, and this estimate like this is not good enough, because somehow neither of these objects is bounded when you want to take the limit, for example, okay? Or you can look at here, neither of these two objects is bounded, okay? So was that your question?
Yeah, I was mostly confused by the norm of Z naught.
Yeah, but even this will cause you a problem. Okay, this causes a problem because it's the L4 norm of a Gaussian process which is stationary. So in every I will comment, but essentially both are yeah, you cannot do anything with this formula, but it's the right direction. And actually I can do it right now. Then maybe you can ask again after I finish. I think, yeah, it's good to take the infinite volume limit. So let me do it because we are at a point. I think it's easier to take the infinite volume limit. I wanted to show the fact that the initial condition do not play a role after a long time. So there are many things now that I wanted to show. So let me just start from the infinite volume limit. Oops. Just to see this, how this, for now we have done things which looks trivial, but somehow we arrive at a point where also more difficult things become quite easy. Okay, what happens when we want to take the limit m going to infinity? The estimate is not good enough. Okay, so this estimate is not good enough because both both objects, so both the L2 norm of Z0, for example, okay, and the L2 norm of YS, if you want. Okay, this is the L4 norm. This is not the probability space, sorry, okay? I'm meaning here the norm, the spatial L4 norm, okay? Do not have, cannot remain finite since both processes, both random field are stationary. Okay, so these are stationary random fields. So it means that in any point of space, you see the same thing. So they're of order 1 everywhere. Okay, and then you are summing over all the space. And that gives something which is the size of the space. Okay, they are not going to 0. So that's very different from what happens in PDE theory usually. Okay, in usual PDE theory, you work in the full space, but when you work in the full space, you think about that nothing is going on at infinity. Okay, here everything is stationary. So everything, like what's going on here, it's going on also in New York or in Paris. Okay, Paris, or in Milan, whatever, in Rome. Okay, so in every point looks the same. So when you try to compute these very extensive norms, you don't have any chance. Okay. However, we can modify our a priori. I think in 10 minutes I can do that. No, a priori estimate introducing a weight. Okay, so of course I'm too greedy. Okay, I want to control the size of the field everywhere. That's not good. Okay, that's not good. And I cannot divide by the volume because then this will not tell me anything about when you try to use this kind of norm in the tightness will not tell you anything. So you introduce a weight, let me call it, did I use rho for something else? Maybe not. And you just introduce a spatial weight. Okay, so now this is the, maybe I have to put a constant here. I don't remember. Something like this, okay? A polynomial weight. That would be enough for taking the infinite volume limit, for example. With C positive since sigma positive, okay? So polynomial weight is just a function on the full lattice. So now it's the full lattice. Let me. In order, so let me make a preparation, okay? In this section, we explicitly the dependence on M because we want to take the limit and use lambda epsilon for the full lattice. Okay, moreover, we extend any periodic field to the full lattice, okay? As a periodically. Okay, so you look at this object just a function in the full lattice, and then I work in the full lattice, okay? Yeah, so here I was mentioning the norm, but the norm that were appearing before, it's really this norm, okay? So, and one expects that, okay, this is true, okay? These two objects are of the size, these two objects are of the size of M to the D, okay, essentially. So no estimates, okay?
But previously we are on a torus and there's no origin, right?
Yeah.
And the norm of X is
yeah, I have to fix an origin, of course, to do this. Yeah, you're right. Yeah. We fix. Yeah. Actually, I have a very pedestrian idea about the torus. Okay, for me, the torus is just there is an origin in the torus I have in mind, but you're right. Okay, a priori there is not. Okay, I always imagine the torus as just a subset, and just that when you fall back on one side, you get on the other side. But you're right. Okay, we fix an origin. Okay, and embed. Yeah. Okay. So, you just embed any function of the torus you write in the universal cover, whatever. But you have also to fix an origin because I cannot control the field everywhere, okay? So I have to decide that controlling it in Paris is more important than controlling it in Milan, for example, okay? And then I fix the origin in Paris, and then this distance is the distance from Paris, okay? Where X is the distance from the origin of lambda, okay? So lambda is not anymore periodic, okay? Only the, so I don't write epsilon, I just write, this is lambda, okay? Yeah, you're right, okay, that's one point. But, okay, but everything else works the same, okay? Now you look at this solution, they are around, and now we test the equation for Z with, with rho Z, okay? And we get, and you get essentially this, now you think what you get, but essentially you get the same estimates, okay? So let me write maybe the estimates, the equation. When you test, you get this, okay? Now I have to change a bit. But now, okay, here, I maybe for some of you, it's boring all this, but I try to be a bit, just in this very simple situation, I can give all the detail. Then later on, I will have to bit run because if I write everything, you don't understand anything. But here, somehow, the idea is that everything looks the same and these things are in the norms. Of course, I cheated a bit. I cheated a bit because you see, you will have rho Laplacian Z, and then I integrated by parts the Laplacian. So you have actually an additional term here, is a constant which depends on rho, and yeah, I'm sorry for that. And which depend on rho zeta square. Okay, so you have to choose the weight in such a way, but essentially that works. Okay, where C rho is a term coming from the integration by parts. Okay, so just let's keep it there, and actually you can make it small as you want essentially, but actually I need to choose a constant here better. Yeah, because so this make the function very constant. Okay, so you can make this very small. Okay, which can be made small by choosing a large or small, L small. Okay, you don't care. Okay, and where? Okay, you have this. Okay, now all these norm are like weighted norm. Okay, you sum over all the points again, but still, okay, you just sum. Okay, this row you can. Okay, I put it inside. So let me, yeah, let me just write one square row just because I want to have the things in the right way. But then here I have to put 1/2 to get right the powers. And here it's okay, but again, it's okay. So just multiply with the weight. The weight somehow it's going to 0 at infinity. So there is some chance that all these sums are finite because this weight is going to 0. Why it's enough to choose it? You could say I take it. I take it of bounded support. Could I take it of bounded support? No, okay. Let me take like this because I will think next time. Okay, but that's a legit question. Okay, why polynomial weight? Why not of bounded support? So if you have an answer, give me. Okay, I think maybe in this case I could take of bounded support. And using similar estimates as above, we obtain the a priori estimates. So now one has to be a bit careful about the weight, okay? But it's not more difficult. So here, sorry, I go back just to take the estimate. So it was something like this. Okay, so the right-hand side, you have the right. So you see what you have the right to use G, and in particular you have to write the right to use this, okay? And then you get estimates. Now you get weighted estimate. And you have rho of X here, whatever. So let me just write this is the L2 norm, is this L2 norm of Z, okay? And this is now on the full lattice, okay? Everything now it's on the full lattice. Okay, I sum over the full lattice, okay? Yeah. So you get all these things, and here all the norm depend on lambda, okay? But okay, just to be precise, because that's a point that is changed. But I have the weight, so it's okay. The weight has to be large enough, yeah. Cannot be small, otherwise it's not clear that it's large enough. Okay. Okay. Now you can take as large as you want. It's not a problem. And you have this, and now you have that. Here you have a way. Okay, here now you have to pay attention what you do. Okay, imagine you take this quantity. So let me try to guess. That's not. Imagine, for example, one of them, the easiest. Let's take that one. Okay, so imagine you want to bound this. Okay, and then what you write this as well, this is y cube already, okay? And you have z, but of course you have in G, you have power 4 of z, but every z is coming with row 1/2. So you have to split this row and you put 3/2 here and 1/2 here. Okay, so now you have something like this, and now you can use like older, Cauchy-Schwarz older inequality. Okay, and then Young inequality, and then this give you. So if you use older now, I think it give me y L4. Then okay, give you L4. And then when you split, you can have a small constant here, but then you need a large constant here, essentially 1/delta. Maybe there are some constants around, I never remember them. So let me just write in this one. Okay. It's something like this. Okay. And then this you can reabsorb. This is how you do. Okay, and this you can reabsorb in G, because in G there is this norm. There is a lambda in front. Let me write lambda, because the lambda is going where it's going. Lambda, where you could put lambda here and lambda there, and then you can put in G, because in G there is lambda. Okay, so you can just write like this. Okay, for any small lambda, small delta. Okay, because you need delta small, because you don't have more than 1 G here, so you are spending delta of G, and that's fine if you can take it small. Otherwise, you have to pay attention. Okay, and then you get an estimate like this, but of course then I have to correct my estimate. Here you have row 1/2, and the constant depend on delta, but you don't care anymore, because you can choose delta 1/2, for example. Okay, as a consequence, one get the estimate. So now you get the same estimate. Sorry, I just copy it. Yeah, let me finish. Maybe I need 5 minutes just to finish this part. So I will go back to it. Now you get the same estimate, but priori discrete M. Wait. You get the same estimate, but now you have a weight everywhere, which you like. So you have rho, but you see the different norm get a different weight. So L2 get rho, but L4 get 1/2. Okay? But now these are things which works in the full lattice. So now the estimate itself does not depend on lambda. You have some choice. Okay, now you have the problem. Okay, so now the first problem. Let me solve two problems. Okay, we have seen that we can construct a stationary coupling of YZ. Okay, so we can use here this stationary coupling and take the average of this equation, of this inequality, to get what we get if we take the average of this inequality. Let's say you take average here, you take average here, you take average here, you take average here. Okay, you can invert, you can, of course, and what you get, these two are equal, okay? But by stationarity, we also have this equal to that, okay? The law Z is stationary, so at time 0, it's equal time and every time. So the initial condition disappear. Yeah, that's very surprising, actually. But yeah, okay. And then you get an equation like this, and everything is stationary. So actually, and again, by stationarity, one gets. So this is stationary, so do not depend on time. So you can just integrate and you just get, this is whatever time you choose is smaller than twice that. Okay. And you can even do it at time 0. Okay, so because you can do it at every time, which gives us a very good a priori on the law of Z0, okay, which are independent, of M. Indeed, why they are independent of M? Okay, well, the only thing which depend on M here now, it's okay, the two laws, okay, but that's fine. But let's see what is this norm. So what is this norm? Is the expectation of the sum over all the infinite lattice. This is an infinite sum, but you have a weight, and then you have y0 x 4. And now you use Fubini. Now I hope it's clear what's going on now. You just replace, exchange, and this is stationary. Okay, so this is a constant time this thing, since y0x is okay, is translation invariant. Okay, so since the law does not depend on x. Okay, and actually one can show okay, that, so let me finish. This is our first Gaussian computation. Okay, how you, now I want to show, I still have a problem here. Okay, so this, okay, this is finite because I can choose the weight which goes to 0 fast enough. Sigma is greater than D. Okay. Okay, if sigma is greater than D, then this is finite and uniformly in M, and okay, uniformly M, provided this is finite and the law of y0 is translation invariant, so do not depend on x, and actually one show that, so we have to compute this, but okay, that's not a computation. So now let me remark. So the point is that Gaussian random variable have all the moments are comparable. Okay, so this is certainly less or equal that the second moment, and the second moment I can compute. I told you I have a formula for that. So this is like m squared minus Laplacian to the minus 1 computed xx, but you could compute wherever you want. So let me say just less or equal. And what is that? Okay, this is less or equal. Then you can compare with the integral of, sorry, yeah, it's an integral, but remember that you are on a lattice. So it's, yeah, it's finite. Okay, just to check that it's finite uniformly. Okay, because this converges to some, so it's some integral. Okay, let me go back. Sorry, I just go back a lot. You know that it's not very nice to you, but I wanted, yeah, I needed, sorry, I don't have it here. Where is the formula? Yeah, so I had this big formula for, I could even write it down. So what is this? Well, this is big formula. So, but let's see it because maybe we understand. So here now you have m epsilon and there is nothing here because this is computed at the same point, okay? And now you see that what is going on, this is converging to an integral, and the integral is made in this domain essentially, okay? Because everything is nice. So you see, as long as you keep epsilon finite, this is just a finite number, okay? It's away from zero, so this is strictly S plus infinity, uniform linear. Okay, so this gives you uniform control. So lemma. So what we have obtained for any m positive, we have that nu is distributed like y plus z 0, okay? Nu of m is distributed like, okay, now I write the dependence, okay, because now it's important, okay? So this is the what I have. This is what I want to study. This is my stochastic quantization representation where y0m is distributed like mu and mu m if you want. Of course, there is epsilon, but let's ignore it. And z0m is a random variable such that, okay, I don't know the law, but certainly I know what I found, that this sup over m of G0m is finite. And this gives tightness. Okay, so we proved that this is a key estimate to take the infinite volume limit. Because at this point you can use tightness, okay? This family is not moving much, this family is tight, and since it allows to use tightness on the family nu m, okay? So that's, I think, a first important point of the discussion. So infinite volume limit is, the proof is finished here, essentially. Because in this way you can have tightness, you can prove there exists an infinite volume limit, okay, random variable, because you have a risk, okay? Here they're unbounded random variables. So you have to prove that somehow as the volume go to infinity, locally this random variable in the topology of local convergence, okay? In the topology. So I stop here because I'm always a lot out of time. Sorry for the delay. On Monday, I will go back to this point and maybe write the details for that, and and then we try to address maybe the problem of uniqueness if I manage, or we go directly to the problem of epsilon going to 0. Okay, but I hope that this already show you some other this technology. I find quite powerful because somehow there are not so many ways to take the infinite volume limit. Okay, this is quite cheap. Okay, essentially part of the preparation is just this estimate. Okay, once you have done this estimate, that's done. And the fact that it's cheap, it's useful because then you have to apply in a very complex situation. So it would be better to be easy at this level because so it will be complexified later on. So I stop here.